Yes.
If I wasn't English, everybody, can I walk over there and
What's that?
can I walk over there and get my makeup since I was English?
If you don't want to walk, I have to sit in the front there.
Why don't you step?
I'm aware of it too.
Okay, listen up. I'm going to do a couple things while you're passing back the homework assignments, which Aaron is going to collect in a minute. Pass your homework assignments to the back. Those of you who aren't here, make sure you turn in your composition about water today if you want it to be on time. We're going to be going over the test from last Wednesday, which I forgot in my house on Friday. I meant to go with you there. So let me pass these back to you. This was a 50-point test, guys, so I only made it 50 points because of the brevity of the test and the fact that it was only part of a chapter. So the cutoffs for A's and B's on bonus points would be anything over a 40 out of 50 would be a B. Anything over a 45 out of 50 would be an A, okay? So those are the cutoffs, 40 and 45 as far as bonus points go. If you want to know what your percentage is, just double the score. That's on the top of your sheet right here, okay? And that would be the percentage. You got another homework assignment here? Okay, let's take a look at the results here on the test from last Friday. Again, this was gas laws, and I think I've got my solution here. Check your answers real quick. F8. Right? Yeah, I think this is a different test. I'm not sure these questions are the same. Some of the problems might be the same. This is a different test completely. Okay, so let me do it this way. Okay, question number 1 was letter F, which was stoichiometry. Question number 2 is K, which was 8.31 kilopascal liters per mole Kelvin. Question number 3 was H. H matches up to molar mass. Question number 4 was J. J was 0.25 moles, if you calculate how many moles that was. Number 5 was I, molar volume. Question number 6 was B, ideal gas law. And question number 7 was C, a study that relates quantities of reactants and products. Number 8 should look like this. And I'm going to do these out very quickly. Check your answers. Okay, so we start with PV equals nRT. Ideal gas law problem. Solving for pressure. And I'm looking for this. 2.00 moles times 8.31 Pascal liters per mole Kelvin times 248. In this case, you needed to change the temperature into 248 Kelvin over 10.5 liters. Answer is 393 kilopascals. Okay, this was number 8. The key here was make sure you get the temperature into Kelvin, 248. Number 9, what volume of hydrogen gas? This was the same type of problem, but now we're solving for volume. And it should look like, the problem here is we don't know N. So here, on this one, this is probably the hardest, one of the harder problems on the test. In order to get N for this equation here, we need to have number of moles. The problem is that this problem gives us grams, 3.86 grams of aluminum. So we need to change that into moles by dividing by the molar mass of aluminum. And so we look at the periodic table under aluminum, 26.98. I'm going to call that 27 grams. And so 3.86 divided by 27 gives me the number of moles, okay, which is 0.21. Now after I figure that out, now I can put it into here. So you can either do it all in one step or you can do it in 2 steps like this. 0.21 moles, 8.31, blah, 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 blah. The temperature here is 294 Kelvin. And the pressure is 102 kilopascals. Okay, so this was the tricky part here. Remember, grams and moles aren't the same thing. You can't take grams and substitute them into the ideal gas law. In this case, the answer comes out to be 5.4 liters. Okay, make sure you always have your units. If you wrote me an answer and you didn't have units, I took off the point. Okay, number 10. This one's, again, ideal gas law, but now we're solving for temperature. So temperature equals PV over NR. Temperature now equals 143 kilopascals. 1 liter, 8.31, the ideal gas constant. A couple people were messing up the ideal gas constant. And then lastly, the volume moles, 2.49 moles. Okay, in this case, temperature equals 6.91 Kelvin. A lot of people got an answer here and then you tried to change it into Kelvin. Remember, the ideal gas law gives you Kelvin. It's already in Kelvin. You don't have to do anything with this answer because, remember, inside this constant is liters, kilopascals per mole Kelvin. So that Kelvin right there is in your answer. So when you use the ideal gas law and you solve for temperature, if everything, all of your other units are fine, then your answer comes out to be in Kelvin, 6.91. So in the next question where it says what would the same, it basically gives you the same question but asks you what the temperature is in Celsius. All you need to do in number 11 is 6.91 Kelvin. Take the answer from the previous one and subtract 273. Okay? To go from Kelvin to Celsius, we subtract 273. To go from Celsius to Kelvin, we add 273. So that's negative 266 degrees Celsius. Some of you got really confused about that, and you got them backwards and couldn't quite figure out what was what. Just remember, Celsius is always a higher temperature than Kelvin, so you add 273 to Kelvin to get Celsius. No, subtract 273 from Kelvin to get Celsius, add 273 to Celsius to get Kelvin. Okay, so this one was number 11. Number 12, back to the ideal gas law. And this time we're solving for the number of moles. 720, 5.6, 8.31, and 295 Kelvin. Questions? Basically, I gave you one of each type. I gave you one for the T, one for V, one for P, one for N, one in grams. And then the last one here, number 13, just to round it out, another volume one. Number of moles this time is 0.625. Temperature is 358 once you add the 273. Pressure is 74.2. And the answer is 25.1 liters. That's it. Questions? The final question said, what is the definition of stoichiometry? And a lot of you just copied it from the matching section up above, which I forgot it was up there, but good job. Good job, that'll work. Okay? Any questions here? Overall, I had a lot of great scores, so pass those to the back, please, Aaron. If you collect those, put those on the windowsill for me. Why don't you take out your notebooks, and we're going to jump into the next chapter today. I'm looking forward to reading your compositions from homework. Okay? Did you have fun doing them? Hopefully you did. Okay? Hopefully they're not boring and just like another essay. I'm not looking for boring stuff, looking for creative stuff. Anybody want to share something that you wrote about? Either you don't have to read it because I already collected them, but concept-wise, Josh?
Well, I was like 10 years old and I went swimming, and there was a waltz going around the pool, and I couldn't swim then, so I was like going around the pool on the edge, and then the waltz came right in my face, and I let go of the edge of the pool, and I went almost drowned.
Almost drowned.
Yeah.
Cool. So a little story about his childhood. That explains a lot about Josh.
That was another one when I went down. I went down a water slide, didn't know it was on deep end, and then.
Cool. Okay. So we got a little. What do they call that when you have a story? There's a word for that. I always forget the word in English. It's not an analogy. It's a. Not parable. Andrew.
One day, swim practice over the summer, me and my brother were waiting in line doing these things called drills, where we had to jump off the block. And it's like 3 feet off the ground. So it's kind of high. My brother's 6 foot. So it's kind of scary for him. And the water's like 3 feet deep, mind you. So we wanted to be like safe, me and him, because we didn't want to hit the ground and hit our heads. So we wanted to go shoot out as far as possible without going under. Well, I let him do it first. And I was talking with someone. I didn't realize he went until I heard this loud like. And he like got out of the water and his like entire front body was red, all the way down to his legs. Like not doing what you're doing.
Massive belly flop. Right there, splat. Yep. Good. Anybody else have some cool things? Okay. So we're dealing with the chapter on water. Okay. We watched 3 videos about water on Friday. We saw a lot of facts having to do with it. We're going to teach those to you this week. My plan is, I'm not sure what my plan is. Okay, we'll see how it goes the next couple days. We have chapel on Wednesday, so that's going to be a short class. We'll see how much we get done. Right now, I don't have a test on the schedule for this week, which means we'll have a bell work quiz on Wednesday. Have your bell work ready. And probably another quiz on Friday on this chapter stuff. And I'm not sure when the test is going to fall for this chapter. Might have a lab next week, so it might be next Wednesday. We'll see how things go, okay? But there's quite a bit to cover with regards to water. We've watched these 3 videos already. Crash course, the science one. These are some of the 3 things we watched on Friday. Okay, we're going to talk about the uniqueness of water, and I talked Friday about how God gave us water. Seriously, I believe with all my heart that God designed the earth for us to live on. The Bible says so in the book of Genesis. I believe that He made water exclusively to support life. And next year when you cover anatomy and physiology, if you're taking that instead of physics, you'll find out every cell in your body contains something called cytoplasm, which is mostly water. Water is required to transfer everything throughout your body, whether it's the blood, the hemoglobin in your blood, or the electrolytes in your blood to keep you hydrated, or the water in your cells to keep them properly hydrated and transfer energy. Water is important to life, so we're going to talk about the uniqueness. We're going to talk about the water molecule itself and what makes it so special. And we're going to talk about some properties that make water do some really strange things, if you really think about it. Okay, we got some terms to do. We'll cover these today. Hydrogen bonding, surface tension, capillarity, and specific heat. Okay, let's talk a little bit about the uniqueness of water. Now, just a quick question here. Everybody got one of those little restroom passes on Friday? Is everybody here on Friday? Okay. And on that, no? On that, I have a picture of a hydrogen bond. And that's one of the things we're going to be talking about here. Let's look at this chart for a second. This is a comparison of water down here with ammonia, methane, nitrogen, and oxygen. And I want to show you all 4 or 5 of these substances have about the same molecular weight or molecular mass. Molar mass, we call it. Okay, water is 2 hydrogens and an oxygen for a mass of 18. Ammonia is very similar. 1 nitrogen and 3 hydrogens, mass of 17. Methane is very similar. Carbon and 4 hydrogens, mass of 16. And if you compare them to a nitrogen and oxygen, which is what you and I are breathing right now, they're very similar in size. But look at what happens. Look what makes water different. Okay? If we look at what they are at room temperature is usually considered to be 20 degrees Celsius. We call that STP, right? Well, STP is actually 0 degrees Celsius. The standard atmospheric temperature is usually considered to be 20 Celsius. And look at the difference. Which one of these jumps out at you? Andrew? Which one's the oddball? Water. Water is an oddball because it's the only one in this size category of small molecules that is a liquid at room temperature. Why is that? That's what scientists ask. Why is that? Number 2, look at the melting points. Connor, what's unique about these melting points here? Is that good or bad? Somebody raise your hand. Is this good or bad? Andrew.
It's good. It's got like a higher melting point than the rest of them.
Melting point is the temperature at which something turns to a liquid.
Yes, it's like from
This is good, bad,
ice. So
or just different? It's really different. It's hugely different. Look at, here's the carbon dioxide. Well, the carbon dioxide is not on this list, but we could put carbon dioxide on this list as well. Carbon dioxide has a mass of 44. It's a little bit bigger. And we saw carbon dioxide has a temperature of what? Negative 109 Fahrenheit, negative 79 Celsius. And that's its boiling point. Okay? Same thing over here. Look at the huge difference. This is 100, and all of these are negatives. Huge difference. Very, very cold. They claim that on some of the moons of Jupiter and the moon of Saturn, there is liquid oceans of nitrogen. Liquid nitrogen. That's how cold it is. Negative 196, negative 200 Celsius. They must be beautiful, but it'd be really, 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 really cold. Don't know if we'll ever get a chance to swim in nitrogen. That'd be interesting. But it's very, very different. So in your notes, you might want to write down, water is unique because, number one, it's a liquid at room temperature. Number two, it has a very high melting point compared to other gases like it. And number three, it has a very high boiling point. So the question is, what makes water different? What on an atomic scale, what on a molecular scale makes water different? There we go. Okay, you saw this in the video on Friday. Water is the only substance on Earth that exists in all three common states of matter. Name them. Ryan. Solid, liquid, and gas. Somebody tell me where on Earth we find solid water. Andrew.
Ice caps.
Ice caps. Where else do we find solid water? Andrew. In the fridge, ice cubes, yes. Where else on Earth do we find solid water? Besides the ice caps, besides the frozen ice in your refrigerator. David? The North Poles, okay, that's called the ice caps. Where else on Earth would we find solid water? Andrew?
Atmosphere, high up. Little solid bits of ice that make thunder. You know, the clouds.
What's it called?
Um,
Solid bits of ice in the atmosphere.
no.
Snow, good. Okay, or sleet sometimes. Where else do we find solid water on Earth? Help me, guys. I know we live down here in Mobile, so we don't run into it a lot. Huh? David, where? Glaciers. Anybody ever hear of glaciers? Yes, those giant flowing rivers of ice up in Alaska that carve out the valleys. Okay, so lots of it. Somebody tell me where on Earth we find liquid water. Jackson. In the oceans, somewhere else. Amaya. Louder, please. Okay, it comes out of the faucet at our house. Drew. The swimming pool, where else? Lakes, where else? Liberty? Ponds, where else? Drew. Toilets, where else? Liberty. Aquariums, where else? You guys are getting really small. I mean, think big. We're talking about the Earth here. Where on Earth do we find liquid water? Andrew?
Clouds again.
Huh?
Clouds again. Rain.
Rain, yes. Rain when it falls out of the sky. Connor? What, do you need to go use some water? Where on Earth do we find gaseous water? Olivia? Gaseous water. What's that?
Cloud. Dang it.
Clouds. You got it. That's the main one, okay? Gaseous water is called clouds, but also, let's think about this for a second. You're in Mobile. Gaseous water. David? Yeah, we call it humidity, okay? Humidity. Humidity here in the south is gaseous water, say, okay? It's all around us. The humidity is literally the amount of water in the air around us. That's what we call it, humidity. Okay, so that's unique. You don't find that. You don't go to Mars and see that. You don't go to the moon and see that. You don't go to other places in our solar system and see water. Now there is a moon of Jupiter that I think has frozen ice all around it. It's like an ice planet with water ice. And underneath, they think there might be liquid ice. But it's very, 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 very cold place. You would not find gaseous water on the moon of Io, I-O, is how it's called. Okay, also water is less dense. Water floats. In your notes, write down, water floats. Why do, water floats, that's silly. Ice floats. Why does ice float? Again, we're going to talk about this in a second, but water, when it freezes, becomes less dense. Most things, when they become a solid, are more dense than their liquid counterparts. You take any other element on the periodic table, any other substance in the universe pretty much, and when it becomes a solid, guess what? The atoms pack together closer. When they pack together closer, they get more dense, and they sink. Right? If I melt something, the atoms get farther apart, and it tends to be less dense. But water does something very unique. We're going to see why in a few minutes, but it gets less dense. Therefore, that's this dot. Anybody ever see the triple dot sign? It's a triple dot sign that means therefore it floats. So why do we have icebergs floating in the ocean? Because ice floats. Why do we have a north polar ice cap? There is no land underneath the North Pole, but there's a huge pile of ice there. Why? Because it floats. Okay, and if it didn't float, it would sink. And if it sunk, the world's oceans would be higher because all that ice would be at the bottom of the ocean. Okay, very cold place, but it floats. Up north, it protects the fish when ice floats. Ice freezes, it protects the fish by forming an icy barrier on top of the lakes. Okay, here's why. Why does water do all these cool things? And it has to do with the fact that water is covalent, okay? And covalent means there is a sharing of electrons between the two hydrogens and the oxygen. We saw this on Friday in the videos. Hank had it upside down, said it was shaped like a V, an upside down V. Or if we turn it this way, it kind of looks like Mickey Mouse with the two ears. Or you might say it looks like a teddy bear. I don't know how you want to draw it. I generally draw it like this. Oxygen and two hydrogens. Hydrogen, hydrogen, oxygen. Okay, so it kind of looks cool. But it does form an angle. We saw a couple months ago it forms that bent shape. And if I build one here, out of our molecular model kits, remember we get that shape that has H, oxygen, and one more hydrogen. Where are you at? There we go. Remember this shape here. We all built it in the lab we did on the molecular shapes. H2O, one oxygen, two hydrogens. Forms that bent shape. Why does it form the bent shape? Because of these electrons. Okay, so let's make this a little bit fatter here. See these two electrons over here and these two electrons over here. Remember, oxygen has two pairs of unshared or unbonded electrons, and they're going to push away these two hydrogens. So if we're talking about this shape right here, there's two pairs of electrons here and here that push these away. So really it's a tetrahedral shape without two things bonded to it here. If I take one of the black carbon atoms and put two hydrogens on it, I'm going to get the exact same shape that I would have Okay, so if I take a carbon atom instead of an oxygen atom, we get exactly the same shape. It's the bent shape. But remember, on the carbon, I'd have 2 more opportunities to bond 2 more atoms here. On the oxygen, it really rarely forms 4 things. It's almost always going to be either 2 single bonds or 1 double bond. And I have 2 pairs of electrons here. So this picture here is showing me that these pairs of electrons push away those hydrogens. And it's always going to be the same angle. Because of this, we get a polar molecule. Remember, polar molecule says the molecule has poles. It's got a positive side and a negative side. Here and here. And we draw that with that little delta symbol. The little delta symbol is a small little d in the Greek alphabet. And little d plus a plus sign means a partial positive charge, as you see here. And a little d with a negative sign means a partial negative charge over here. So these things act like magnets. They have a pole, a north pole and a south pole, or a positive pole and a negative pole. And they line up and do these really cool things, which means ice floats, which means you get solid, liquid, and gas on Earth all at the same time. Really cool properties. Very high boiling points, very high melting points. And that's because of polarity. It's because of the electron structure. And number 3, it's because of, here's another picture showing the attractive forces between hydrogen bonds. And we'll talk about this in a second. So here's a water molecule. Here's another water molecule. Here's another water molecule. Here's another water molecule. And they all line up. Negative to positive. Negative to positive. Negative to positive. And when they do that, they stick together. And there's a word for that called, looking for it, called hydrogen bonds. There we go. Okay, so write that down in your notes. This is a key word, a key critical word. Hydrogen bonds is what makes water unique. It's the big theme in this chapter. Hydrogen bonds is why water gets bigger when it freezes. Hydrogen bonds is why water has such a high melting point, because these molecules are stuck together and they're hard to rip apart. Hydrogen bonds are why it has such a high boiling point and holds so much energy. So the hydrogen bond is the reason why. And we get hydrogen bonds because of this reason right back here. Okay, because of the polarity, because of the pairs of electrons, and because of the shape of the molecule. So this gives it a positive, negative, positive, partial positive, and then that causes them to form hydrogen bonds. Okay, so a hydrogen bond is a weak intermolecular force between dipoles, remember this word from a couple chapters ago, between the hydrogen and the oxygen atoms. So when you see a picture like this, what it's showing is a water molecule lined up with another water molecule, lined up with another water molecule, lined up with another water molecule, lined up with another water molecule. Okay, you see the little dotted bonds, dotted lines in between them. So when you look at your homeroom, your work restroom pass for the quarter, you've got a little hydrogen bond shown there. Okay, so this is a key. This is what makes life happen in our bodies. It's what makes life possible on Earth. It's what makes life possible in our cells. It's what makes everything happen around us. Hydrogen bonds, really, really, really important, okay, in the world of chemistry. Let me go back here and see what I missed here real quick. Attractive forces. Water molecules have such a strong electrical force they would orient themselves like magnets with the opposite poles of different magnets pulled towards one another. Yes. And that's because of hydrogen bonds. Okay. Now, formation of connection between hydrogen atoms and oxygen atoms is called this right here. So there's your definition of what a hydrogen bond is. Jot it down. Now, I'm going to ask you a silly question. Do hydrogen bonds have to happen between hydrogen? What do you think? Okay, it has to be between hydrogen and something else, okay, but it doesn't have to be between hydrogen and oxygen. Hydrogen bonding always occurs with hydrogen, okay, so you have to have hydrogen there. But if it's not between hydrogen and something else, it has a different name. It's not called a hydrogen bond, it's just called a dipole-dipole force, okay? But a hydrogen bond has to be between hydrogen and oxygen, or hydrogen and sulfur, or hydrogen and chlorine, or hydrogen and fluorine. It's usually between hydrogen and one other very highly electronegative element. All those guys in the upper right-hand corner. Okay, so any molecule that has a hydrogen bond has the potential to form hydrogen bonds. Here's a cool one over here. This is a big molecule. I'm trying to figure out what that is. It's weird. I'm not sure if this is a real picture or not. That's interesting. But you can see multiple hydrogen bonds between this molecule and this molecule. Okay? So the more hydrogen bonds, the stronger the bond between things. This forms a lot of cool things in chemistry. Now, many of the unique properties of water are due to hydrogen bonding. Let's talk about some of these. Okay, remember, here's our boiling points again. -161, -33, and 100 degrees Celsius. It's big. Why is that? Remember, when I go from a liquid to a gas, what happens? My molecules need to break apart from each other. They need to have enough energy to separate and fly away into the air. So part of the energy that needs to be overcome in a liquid is what's holding the molecules together. But because water has hydrogen bonds holding them together, it takes more energy to rip them apart and form a gas than it would for ammonia, -33, or it would for methane, -161. These do not have hydrogen bonds, so they have a much, much, much lower boiling point than water, 100 degrees Celsius. Water, because of the hydrogen bonds, takes a lot more energy to rip them apart. Okay, I'm going to stop right there for today because that's a good stopping point. We've covered a lot having to do with hydrogen bonds. Hydrogen bonds account for boiling points, melting points, floating ice, and we'll see tomorrow more of the properties of water.